Hey everyone, we're going to look at number 19 in section 4.5. Of course, we're going to use L'Hopital's rule to evaluate the following limit. Okay, now remember L'Hopital's rule involves limits of the form 0 over 0 or infinity over infinity. What's the form of this limit? Well, as x approaches 0, we have an exponential expression here. The base is cosine of x. The exponent is 9 divided by x squared. The base is approaching cosine of 0. Cosine of 0 is 1. So the base is going to 1. The exponent, though, what's happening there? It's approaching 9 divided by 0. What does that mean? 9 divided by 0. That's not something we can evaluate. But what's really happening is x is getting closer to 0. So 9 is being divided by, a smaller and smaller value, right? Which means overall, that is going to infinity. In other words, the limit 9 divided by 0, that form is not indeterminate. It's going to infinity. Okay, so we have 1 to the infinity power. This is indeterminate. It is not a L'Hopital rule form, though. It's not 0 over 0. It's not infinity over infinity. It's indeterminate because the base is getting close to 1, and 1 to any power is 1. So the base is trying to get this to be equal to 1. But the base actually is never equal to 1 because as x approaches 0, the cosine of x is getting closer to 1, but it's always a little less than 1. So if you have something a little less than 1 raised to a bigger and bigger power, that's actually going to go to 0, approach 0. So for instance, like 1/2 raised to higher and higher powers is actually getting smaller, right? 1/2 squared is 1/4, 1/2 cubed is 1/8, right? Getting smaller. So this limit could be 1, it could be 0, or it could be something in between. That's why we call it indeterminate. We don't know. So we have to do some work. Now, when you have limits of this form and you want to apply L'Hopital's rule, right, which is 0 over 0 or infinity over infinity, which is not this, we've got to do some work. And that work involves a logarithm, right? We used logarithms in logarithmic differentiation, very helpful there. And it's helpful in these limits here. So what I'm going to do to make that easy, I'm going to let y be the limit we're looking for. Okay, and I'm going to take the natural log of y, which would be the natural log of this limit. Now, I can take the natural log, so to speak, and push it inside this limit or pull this limit out. And the whole reason I can take, or going in reverse, I can take the limit as x goes to 0 and plug it inside the natural log function in this case. And I can do that because the natural log function is continuous on its domain. And remember, as x approaches 0, cosine of x is close to 1, 1 to some power. It's a positive quantity. And so the natural log's domain is everything greater than 0. So we're plugging in values that are always positive. And since it's continuous, we can push this limit through or pull the limit out. Okay, so we can do that for continuous functions. Now, what can we do? We're taking the limit as x approaches 0 of this expression now. Well, when I take the natural log of something raised to a power, remember the property of logarithms we used with logarithmic differentiation. This exponent basically comes down in front, right? Because again, logarithms are exponents. And when we raise the base raised to some power or its logarithm raised to another power, we multiply the exponents, right? That's the rule of exponents. So that's where this property comes from. Okay, so we can use this property to bring this exponent down in front, right? The 9 divided by x squared is going to come in front of this now. And I'm going to write 9 over x squared times this as 9 times the natural log of cosine of x all divided by x squared, right? That's the same thing as 9 over x squared times this thing. And now what do we have? Well, let's see. We still notice I haven't gotten rid of the limit here. We still got the limit. And remember, this is the natural log of y we're looking at, not y. So we'll address that in a minute. So as x goes to 0, obviously x squared is going to 0. And then as x goes to 0, cosine of 0 is approaching 1. So this is approaching 1. And remember, the natural log of 1 is 0. So this thing up top is approaching 0. And so this is finally what? L'Hopital's rule form. Right? That's good news. That's the whole goal. So we started with this form. We've got to get it to 0 over 0, infinity over infinity. How do we do that? By using logarithms and essentially this property of logs. Okay, so let's use L'Hopital's rule. Remember how that works? I like to put the little L over the equal sign when I use it. We take the derivative of the top. Well, what's the derivative of 9 times the natural log of cosine of x? Well, derivative 9 is a constant multiple, and then the derivative of natural log of cosine of x, we have to use the chain rule on. The outer function is the natural log, inner function cosine of x. What's the derivative of natural log? 1 over, in this case, cosine of x, 1 over u, 1 over cosine of x, times the derivative of cosine of x, which is what? Negative sine of x. Okay, so there's the derivative of the top. Derivative of the bottom, piece of cake. Derivative of x squared is 2x. Can we clean this up a little bit? Yeah, negative sine x divided by cosine of x is negative tangent x. And so I've got negative 9 tangent x over 2x. Now, as x goes to 0, what's happening here? Well, obviously 2x is going to 0, right? And what's happening here? Tangent of 0 is 0. Right? You should be able to use the unit circle to deduce that. Remember, tangent is sine divided by cosine. Sine of 0 is 0. Cosine of 0 is 1. So this is approaching 0 over 0. Well, again, what's that mean? Did we mess up? No. It's still L'Hopital's rule form. So use L'Hopital's rule again. I think we can see we're going to get somewhere. If I use L'Hopital's rule again, what do we get? Well, what's the derivative of negative 9 tangent x? We have to remember the derivative of tangent x is secant squared x, right? So negative 9 is a constant multiple. Derivative of 2x is just 2. Well, now what's this limit? Notice I've got the limit still here as x approaches 0. Well, this function is actually continuous at 0 because when I plug in directly, remember secant squared x is secant of that value all squared. Now I'm plugging in x equals 0. Secant of 0 is 1. Right? Remember, secant is the reciprocal of cosine. Since cosine of 0 is 1, the reciprocal of 1 is 1. And of course, 1 squared is 1. So I just get negative 9 halves times 1. And there's the limit. Now notice, what is this negative 9 halves? Go all the way back. This is the natural log of y. Well, what is y? Y is our limit. So our limit that we're looking for is not negative 9 halves, but the natural log of our limit is essentially negative 9 halves. So how do you proceed in solving a logarithmic equation? You write it in exponential form, right? What are logarithms? They are exponents, right, on the base. So when I say natural log of y is negative 9 halves, this is the exponent, negative 9 halves. What is it, the exponent on what base? Well, ln means log base e. It's the natural logarithm, right? So it's e to that exponent, right? That logarithm is what y is equal to. Alternatively, you can think about, let's take e and raise it to the natural log power. It will be the same as e raised to the negative 9 half power, right? Since both of these are equal, but e to the natural log of y is indeed just y, right? That's the inverse relationship between those, and we get that. And so the limit as x approaches 0 of cosine of x raised to the 9 divided by x squared power is e to the negative 9 halves. Now be careful. I said the limit could be 0 or 1 or something in between. Some of you are saying, oh, look, it's negative. So you got a negative number. Something's wrong. No, e to the negative 9 halves power is not a negative number, right? That's 1 divided by e to the 9 halves power. And you can use your calculator to approximate this. This is some number between 0 and 1. Okay, very lot going on in this problem. Lots of calculus with derivatives and pre-calculus, being able to solve logarithmic equations. So you have to be building these skills and working through these things. I hope this is helpful for you on this one. Let me know if not.